Okay, moving on to question 5. Okay, so we're supposed to suggest an appropriate indicator for this titration. Now in this question, they say that it's a weak acid, strong base titration. Remember, it's your lactic acid and your NaOH. So we can either do this by memory and therefore propose phenolphthalein. Alright, we can also use example thymolphthalein, thymol blue, or bromothymol blue. Right, so the 4 indicators for weak acid, strong base titration we can use. That's the appropriate indicator. Okay, so the reason, so this is give a reason, right? So the reason is standard, is quite a bookwork question. We look at the pH transition range of the indicator. So this is a new term over here. What does the pH transition range of the indicator means? And you just not see there were certain values that are bundled together with the indicator. These values basically indicates the pH values in which the indicator will start to change color. So the pH transition range simply means the pH range in which your indicator changes color. Okay, we're going to elaborate this using the diagram below. So what is so important about pH transition range? The pH transition range of the indicator must lie within the region of the rapid pH change over the equivalence point. So let's take a look at this. Alright, so what I've done is to plot the graph and overlay the color of indicators for meta orange and phenolphthalein inside this diagram. So the equivalence point is given by the dot over here. Okay, so the equivalence point, if we look at the data just now, it was somewhere around pH 7.7 around 7.80, right? So what happens is this: if you use meta orange, alright, it's not suitable because the indicator will have changed from red to orange somewhere here. Alright, you can see the pH will start to turn orange at this region. Alright, so which means at pH 7.8, which is the equivalence point pH, the region in which you have rapid pH, change, alright, it will have already turned from red to orange before the equivalence point. So you want the transition range of the indicator, that means the region in which it changes color, this region, right, or this region in this case, to fall within the region of rapid pH change, and it should be over the equivalence point. So phenolphthalein is suitable because you can see at pH around 7.8, alright, this is where phenolphthalein turns from colorless to pale pink. Alright, thymolphthalein will be from colorless to pale blue. Alright, so these two will be suitable indicators. Okay, moving on to B, we are supposed to calculate the molar concentration of lactic acid in the solution. So molar concentration is basically just simply mole per dm cube. So this one we need to use the graph. So how can we get information of lactic acid in the solution? So if you read the question, we have this concentration of sodium hydroxide. And at equivalence point, we know the mole ratio of lactic acid to NaOH is 1:1 ratio because it's a monobasic acid. So at equivalence point, that's where you have equal quantities. So as long as we know how much NaOH we use, we will know how much acid we use, and in 10 cm cube, right? In 10 cm cube. Okay? And therefore we can find the concentration. Okay, so let's take a look at equivalence point. What's the volume of NaOH needed to reach equivalence point? We need 15.60 cm cube. So in other words, we need 15.60 cm cube of NaOH to neutralize the lactic acid. So 15.60 convert to dm cube or 1000. This is the number of moles of NaOH. Okay, so given that lactic acid is monobasic, the mole ratio is 1:1. So the number of moles of lactic acid in 10.0 cm cube. Alright, why 10.0 cm cube? Because that's the aliquot that you use, right? It's also equals to 7.80 times 10 to the power of minus 4. Okay, this is given in the question, right? Moles. Okay, so number of moles of lactic acid in 10 cm cube is this, because it's 1:1 ratio. Okay, so to find the concentration of lactic acid, we use the number of moles, 7.8 times 10 to the power of minus 4, divide by what's the volume? 10 cm cube. Alright, 10 cm cube lactic acid originally. Alright, so this is the concentration of lactic acid, 0.0780 mole per dm cube. Okay, so now we're going to move on to the initial pH. question and use this to determine the degree of dissociation. The initial pH is given as 2.5, so pH is 2.5, right? We're supposed to use this to determine the degree of dissociation of the lactic acid. Okay, so pH equals to 10 to the power minus 10 to, log 10 H plus with the power 10 to the power minus 2.5, and therefore this is the concentration of H plus. This is just a simple application of your formula of pH, right? You just make H plus a subject now. 10 to the power minus pH is your pH plus concentration. And in the case of degree of dissociation, we know that it's basically the amount of acid dissociated over initial concentration, which is the same as, right, if you look at the equation, right, the amount of H initial change at equilibrium, we look at concentration, right, we have X of then 0, 0, and minus Y, X minus Y, then Y, and Y. So we calculate degree of dissociation alpha will be equals to Y over X. Alright, the amount of HA dissociated over HA initial, which is the same as your H plus concentration over your HA initial. Okay, so H plus we have 3.16 times 10 to the power minus 3. Okay, we divide by the concentration of the acid, which is found earlier on, this value here, right? Lactic acid initial concentration, 0.0780. Therefore, we get 0.0405. This degree of dissociation, we do not have to multiply by 100% because we are not calculating percentage. When it's percentage, then we will multiply by 100%, and therefore we get around 4.05%. Okay? Okay, now we're going to move on to D, deduce from the graph the Ka of the lactic acid. So let's take a look at the graph then. Alright, what can we use which part of the graph can we use to determine the Ka value of lactic acid? So in this case, we will make use of a very special point. Over at this region is a buffering region. Alright, we know that at the buffering region, there's a particular point in which you can find pH equals to pKa. Alright, so remember pH equals to pKa, and this region is when we have maximum buffering capacity. Alright, pH will be equals to pKa, and this happens when your salt concentration is equals to your acid concentration. Okay, so recall, so this is your understanding of buffer, maximum buffer capacity. The amount of conjugate base and the weak acid is the same. So this will happen typically, alright, if the buffering region is before equivalence point, it will happen at half of your equivalence volume. Alright, so if 15.6 is the equivalence volume, 7.8 over here will be the half equivalence volume. Read off the graph, you get about pH of 3.8, right? Two small squares away, 3.8. Okay, so pH will be about 3.80, and that's equals to your pKa. Okay, so that's what we're going to apply here. So maximum point of maximum buffering capacity, it corresponds to 7.80 cm cubed, which is half of 15.60, which is half of your V equivalence. Okay, so the pH at the point in time is equals to pK is 3.80. To find Ka, 10 to the power minus pH, or 10 to the power minus 10 to the power, to be more exact, is 10 to the power minus K, pKa, and 10 to the power minus 3.80. Therefore, you work out the math, you get 1.58 times 10 to the power minus 4 mole per dm cube. Okay, at this juncture, okay, I will present another way to get the answer. Okay, so deduce from the graph, we know that initially, given in C, right, the initial pH is given as 2.5. So, so this is another method, at initial pH of 2.50, okay, you only have your lactic acid present. So we can basically make use of this formula, H plus equals to square root C times Ka. Alright, so what's the H plus at initial pH? Will be 10 to the power of minus 2.50. Agree with me? Because pH and H plus is linked by negative log 10. Equals to square root C. In this case, we know from part B, what's the concentration of the lactic acid? 0.0780. So 0.0780 Ka is the one we want to find. So some simple mathematics. So Ka will be 10 to the power of minus 2.50. We square it over 0.0780, and therefore we get a value of around 1.28 times 10 to the power of minus 4 mole per dm cube. Okay, so you can see the Ka from this method 2 is somewhat similar to that of using the point of maximum buffering capacity. So this is your method 1 and your method 2. Okay, both are possible solutions to this question. Okay, if not, move on to E. In E, we're supposed to explain with the aid of a Stokes equation why the equivalence point of this titration is in alkaline region. So equivalence point, right? And we're supposed to use a Stokes equation. Equivalence point, what do we have? Remember, in this case, your RCOOH and NaOH has formed your salt, RCOO minus, Na plus, and H2O. At equivalence point, you have no more acid and sodium hydroxide remaining. Alright, both are in stoichiometric quantities, right? Stoichiometric quantities. What you have left is just the salt and the water. And they say that why is it at the alkaline region? So we take a closer look at the salt. What's the salt? The salt contains RCOO minus Na plus. RCO minus compared to RCOH. Right, RCOH is a weak acid. RCO minus is the conjugate base, and this conjugate base can therefore undergo hydrolysis in water. Alright, so hydrolysis of the salt causes the pH to be non-neutral. That should be your thinking. So what's the conjugate base then? So RCO minus, right? So in this case, the R is your CH3CH CO2 minus. Right, so this is your R. Okay, undergoes hydrolysis, and in this case, because it's a conjugate base and it must give an alkaline pH, it must undergo hydrolysis to produce OH minus. So let's write the formula. This, alright, undergoes hydrolysis in water. So water, what can be formed? So since it's functioning as a base, it must be a proton acceptor. So because this is functioning as like a weak base, alright, it's a conjugate base, right? It's a weak base. So we'll write a reversible arrow. Okay, a reversible arrow to show hydrolysis functioning as a weak base. So after accepting a proton, it will produce COOH and OH minus. This OH minus is the one responsible to cause pH to be alkaline. Okay, because OH minus will be more than that of HCO plus, and therefore pH will be more than 7. Okay, so some of you may be confused. Sure, in this case, why can't I view it as this reaction going backwards? Yes, this reaction does goes backward and forward, and that's why you have a reversible arrow. But at equilibrium, you can take a look. There is no H plus produced from this reaction. What you have is only the OH minus. This extra OH minus causes HCO plus to be more. This OH minus at equilibrium is the reason why you have OH minus more than HCO plus, and that's why pH will be more than 7. Okay, moving on to the last one, we look at the acidic buffer solution. Alright, it's one which makes up of weak acid and salt. So must contain the weak acid and the salt. Where can the buffering region be? So recall we analyzed this question earlier on. In this case, lactic acid is in the conical flask. This can happen only when you still have some lactic acid remaining. So this must happen before the equivalence point. So as a rule of thumb, why do you circle the region? I will typically ask my students to circle, to highlight a half equivalence point value. Alright, so this is what we mentioned just now, half equivalence volume. And you circle the region around it. Alright, you do not draw a very big circle like this. No. Alright, you just circle a small region that's around the maximum buffering capacity. Alright, so this corresponds to your maximum buffering capacity. Alright, so this way you can circle your buffering region. Okay, and with that, we're done with question 5.